Recording has started by now. So welcome to the session 6, where we will discuss some practice problems of week 6 of the Parameterized Algorithms course offered in 2024. So let's look at the questions. And this is also going to be related to Treewidth and the use of Treewidth for designing dynamic programming algorithms. So I'll let you look at the question. So there are some terms which need to be discussed.
Yes, so I remember the tree decomposition part, and I remember the idea of the bags, and
Yes,
I remember that the count of the elements in the largest bag becomes the tree width.
minus
So
1. Yes,
minus yes -1, and some of the terms needs to be introduced.
yes. So we also have seen what is a simple tree decomposition where no bag is a subset of another bag. Uh,
Yes.
yes, so tree decomposition and simple tree decomposition are discussed. So we must understand what is a nice tree decomposition. But before that, let's uh, understand what the question is asking at a high level. So a graph G is given and it's one of the rooted tree decomposition is given. So this is shown in the picture. And now we are converting this rooted tree decomposition into what is called a nice tree decomposition. And then there are some steps, some algorithm which is discussed in the video that, okay, these are the steps that you have to follow to convert a given rooted tree decomposition into a nice tree decomposition. And step 1, step 2, step 3 are shown. And there are some remaining steps which have to be carried out. And on execution of those remaining steps, you will find what is uh, a nice tree decomposition. And the question is, which one of these four options is in fact the nice tree decomposition of the given tree decomposition? So first, let us understand what is nice tree decomposition. So we have seen tree decomposition. We have also seen simple tree decomposition. And now we want to understand what is a nice tree decomposition. So let me open the definition for myself. Okay, here's the definition. Rooted tree decomposition is called nice is nice if every node X is one of the following four types. Right. So I will highlight nice. So what are the four types? Type 1 is leaf. So that means, uh, okay, so what is a leaf? Leaf is a node X with no children, and the back size of the leaf should be 1. So that means in the back of the leaf node, exactly one vertex should be present. So diagrammatically, so here is a leaf. It contains one vertex and it doesn't have any children. So maybe it can have parents, of course, it can have parents, but it doesn't have children. That is the first type. Second type is introduce. What does introduce mean? So it means node X which has one child Y. So X has one child Y, and additionally, the bag of X contains exactly one element more than the bag of Y. So B is X is a bag of X. This is bag of Y union additionally one vertex B. Okay, for some vertex. All right. So diagrammatically,
So can you explain this introduce term again?
so introduce means there is a node. This is X. So this is a bag of X. In the bag of X, let us say there are these three nodes, U, V, and W, and it has only one child. The child is a bag which has U and W. So compared to the bag of child, there's one node extra
Oh, yes.
in the node. So therefore, this is an introduce node.
Okay. So does this mean that this bag X is introducing the element B?
Yes, exactly. There is a difference of exactly one element. So at a time, exactly one element is being introduced. It's a completely similar idea, complementary idea that is called forget. Exactly one element is to be forgotten. So what is a forget node? So a forget node is a node where it has one child, but in the child there is an additional node. So I will just copy the same thing and I will sort of leave with it. So in this node, so UW is here and UVW is here. Okay. So what is it? I'll write it down. So one child Y, and in the bag of X, there's one element missing than the bag of the child. Okay. So is a forget node concept understood?
Yes, yes.
Okay. So it's just the opposite thing of introduce. So one node is being forgotten in this node. As one element is being forgotten in this node compared to the child.
Yes.
And the last thing is called a join node. So a join node is a node having two children, y1 and y2, such that the bags of both the children are exactly same. Bags of both the children are exactly same. Okay. So this is a forget node. So what happens here is his, let us say, UVW. Again, its children are also UVW. So this is going to be called a join node. So what is a nice 3D composition? If you observe this pattern, if you look at the 3D composition and you realize that every node is either of leaf type or an introduce type or a forget type or a join type, then you will conclude that wow, this is a nice 3D composition. So that is the definition. Okay,
Yes, and the nice tree need not to be a simple tree. Because in the simple tree, I mean, no node can be the subset of the other node.
that is correct.
Yes.
That is correct. So nice and simple are there are no implications that if it is nice then it is simple and the other way around. But the question is first is why are we interested in a nice 3D composition? The answer is it helps us do dynamic programming, design dynamic programming algorithms in a structured fashion. Uh, and second is whether given any 3D composition, it is always possible to obtain a nice 3D composition out of it. Okay, so there is a
Yes.
yes. So first question is already answered that for enabling ourselves to do dynamic programming in a more structured way, we are interested in this nice 3D compositions. And then the question is it always possible to find nice 3D compositions? So answer is yes. So a 3D composition of width, width means backside minus 1, a 3D composition of width W and n nodes, can be turned into a nice 3D composition of, let me write it down, can be turned into a nice tree decomposition decomposition of same width, that is same back size, and add additional W factor more number of nodes in time order width square n. So the running time is also not too much. So if width is constant, then sort of linear time, we can obtain a nice 3D composition. We can obtain a nice 3D composition from a given rooted 3D composition. So that is also a good news that in almost if W is constant in linear time, we can do this transformation.
Okay, and the W used in the orders is same as the width or something else, or is it a constant?
It's width.
Okay. And inside this big O notation, so order of Wn, so W here also stands for the width only or something else?
Width.
Width. Okay.
So if the width is constant, then we can do it in linear time. If the width is super constant, more than a constant, then there is dependence on width in a more uh, predominant way. Okay. All right. Now we are ready to see the question and see understand uh, what the question is asking. Okay. So here is a rooted tree decomposition having three nodes. So what is the width of this rooted tree decomposition?
2.
Right. So we want to obtain a nice tree decomposition from this. So the first step, what they do. So first, first appreciate that the current tree decomposition is not nice because look at the root node C comma D. If it has two children, then in order to become a nice tree decomposition, these two children should have the same backs. So it should be a join node. If at all, it has to be a nice tree decomposition. But then this is not the case here. So we want to
Yes.
convert it. All right. So then, so first thing, let me copy this diagram. We'll copy this, and then the remaining steps we will perform. First, let's see till what point. So they're running this algorithm of converting a rooted tree decomposition into a nice tree decomposition. So we will first see how much they have done, and then we will do the rest of the things. What happened? I copied it. Okay. Is the font large enough to be able to read?
Yes, yes.
Okay. So the first step, there were three nodes. The first, they realized that, okay, so any leaf node should have exactly one vertex inside it. So this leaf has two vertices, this leaf has three vertices. That is not allowed in order to be nice. So how we shall take care of the leaves? That is the first uh, objective. So they said, okay, so from CE, drop one of the elements. So you can drop C. So if you drop C, then you get this single element node. So make it a leaf, and the original node becomes an introduced node because it introduces C for the first time. So with this introduction, so rather I would say with this uh, transformation, they're able to take care of one of the leaves. So this leaf had two nodes, two elements. Now they have two leaves. This leaf is yet to be taken care of, but this leaf is taken care of, and its father, or rather its parent, is also following the uh, introduce node convention, that it introduces one element, and also it has one child. If it has two child, we won't call it introduce node. So this is taken care of, this side. Now we have to take care of the other leaf node. So to do so,
I have a question here. That instead of introducing C, we could have introduced E also. So by
exactly, you had the liberty to do so. In order to obtain a nice tree decomposition, you just have to ensure that these four types of nodes are in your decomposition. So it is possible that you end up with getting a different nice tree decomposition than what I get.
okay,
But our purpose is just to get one of these nice tree decomposition so that we can run this dynamic programming algorithm. So in terms of running time, it will not make any difference as to what is the exact uh, uh, nice tree decomposition. What will matter is what is the structure of the nice tree decomposition.
yes,
So now we have to take care of this leaf node. So they do this, they have written what they have done. So they say, okay, from ABC, we generate a child AB, but that is not the right leaf, because in the leaf we allow only one element. So again, drop one node and make this child A. So from ABC, you drop C to get to AB and make it a child of ABC. From AB, you drop B to get another node A and make this a child of AB. So now this is a valid leaf because in the leaf bag, there is exactly one element A. And this is also a valid introduce node because it is introducing B alone. This is also a valid introduce node because it is introducing C alone. And they have single child. So therefore, these sides and these sides are taken care of. The problem is now, where is the problem now? That is causing us, uh, uh, that is not letting us calling it a nice tree decomposition. Why is it still not nice?
yeah. Because what about the root node say CD? So how would we classify the node CD?
Yes, yes, yes. So this is neither introduced. So,
Yeah.
so now there's some echo. All right. Yeah. So now CD, this is having two children. But since it has two children, therefore both the children should have the same bag. That is, it should be a join kind of node. So we have seen that if at all there are two children, then the child, the two children's bag and the parent's bag should be identical. That is not the case here. So now we have to take care of it. So they did some what? So they said, okay, CD, let us make two children, which are the identical bags. CD has CD and CD. But then once you introduce the two children, uh, the other thing that you have to ensure about is that whether these two children are also classifiable into one of the valid types. So now is this now since it's a single, it has a single child. So R dash has a single child. It has to be either an introduced node or a forget node. So with respect to its child. So with respect to its child, can we say that this is an introduced node or a forget node?
No, no, neither this is an introduced node and nor forget.
Yes. So we have to take care of this as well as R double dash also we have to take care of this because it is neither introduce nor forget. Okay. Okay. So in order to make it, let us say, introduce, its child should be either a bag containing C or a bag containing D. Okay. But then we want to introduce a child that is going to make R dash. So we want to make, let me write it down. So our objective is now, right now, is to make R dash an introduce node, let us say. Okay. So therefore, R dash should have a child which is either C or D. All right. But then after we introduce this node here, T1 is a child of this node. So T1 is the child of this newly introduced node that we are intending to introduce, so that this becomes introduced node. So whether it is beneficial to take this or this as the child of R dash. So here, shall we introduce C or D?
At which point?
Between R dash and T1, we want to introduce a node.
Oh, so
So
then,
that,
yeah, yes.
yeah,
So including C would be beneficial because then one node will become the introduced node and the other one will become a forget node.
very nice. Yeah, that's exactly what we have to do. So we will draw this. So okay, what happened? Okay. So introducing C is the right thing to do. Let me just write it down. Just let's take this thing. Uh, so if I introduce C here and make this a child, it's getting small. Uh, okay, I'll redraw this. So we had the root R. R's children were again same bags R dash and R double dash. And then we realize that R dash is not an introduced node. We want to make it an introduced node. So we introduce this node C, and then C becomes the parent of, let's say this is T1. So we have to give C also a name. Let's say this is X, node X. Now, as far as the left subtree is concerned of this tree decomposition, uh, have we achieved a nice tree decomposition in the left side?
Yes.
Yes. So this is join node. This is introducing D. This is forget node because it is forgetting E. This is an introduce node. It is introducing E. This is a leaf node. So the left side we have taken care of. Okay. So now we have to take care of this also. So I can draw ABC, AB, but I will draw it slightly later. But we have to take care of this. Okay. Again, so we want to make it an introduced node. So we have two choices. We can take C or we can take D and make it a child. And but after whatever we take, we have to introduce ABC, and then ABC has to be taken care of also. So we should take C or D. In this place, should we have C or D? That is the question. In order to be able to take care of this entire right subtree.
Yes, so if I introduce C here, then I would be introducing D, but then below this, I need to forget something. So then, but if I include D here, then I would be introducing C, but then what will I forget? So again, I think that introducing C is beneficial, but then after C, we'll have to include something more also, uh, that, in,
Yes,
that includes A and B kind of thing.
correct. So there should be some introductions, some forget. So we have to finally get down to A, which is the leaf node. So A should introduce something. So in multiple layers, introduction has to take place, and then in multiple layers, forgetting has to take place. But D is not going to help us, because if I take D, I am introducing C here, but below D there is only ABC. So whereas if I had C here, then if I could take sort of, let's say, BC, then I can call C a forget node. But in order to call D a forget node, I have to do more work. So therefore, let us stick to C.
Yes.
So the similar thing we are going to do. Let us say introducing C. So we have to give it a name. Let us say we call it P. But C's children are ABC. So that is not helpful. So we have to drop one of these things in order to make C a forget node. Okay. But now we can drop A or B. So we have the choice, which one shall we drop. Now we have to be a bit careful. So the last thing that we want to retain as a leaf is A. Okay. So so the parent of A should be A comma something else. Okay. So therefore, dropping A at this point, is that a good idea? Because see A. So let me put it this way. So we have ABC. So this part is fine. So from ABC, we drop something to get. Uh, so here we have to retain A. So we can keep C or B here. Uh, so you have to do some trial and error. So if I take C here, then so from here, can I keep AB? Is this a valid thing? Oh no, two things cannot be introduced. There are two things. So C has to be kept here. So C comma B or C comma A will do. What does this look like? C is a forget. BC BC is a forget in terms of its child with respect to its child. This is an introduce with respect to its child, and this is an introduce with respect to it. This is a, yeah, this is good, but it need not be the unique way of doing it, as I already said. See, one could also find a different thing. For example, one could also do this thing. For example, let us say instead of C, if I had introduced B here, that will also do, isn't it?
Yes. Instead of here, instead of, so this is right, but then instead of CB, what did you say? I could not hear.
Yeah, I said that. So here I have the liberty to have B or C.
Yes, 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 yes.
but then we will check that what is the answer. So here I have the liberty of B and C, and let us now see that what is the option. Now, depending on what is the option, because there could be multiple correct answers, we have to decide that how we shall proceed. So let's look at the options. So this side is more or less fixed. Let's worry about this side. So let us say B is here. So A to AB, AB to ABC, ABC to BC, BC to C, then again CD, CD. Let us see if there is an option like that. How many nodes are there? 1, 2, 3, 4, 5, 6, 7. So including the root on the right side, there is 7. Okay.
Yes, so I think that this option is correct. This one is correct.
Yes,
Uh,
yes, yes. Last. So yeah, the last one is not correct. The second last, this one is correct. Huh. So answer is this is accepted answer. So on the left side, the same thing that we got. On the right side, including the root, there are 7 nodes. So A to AB, AB to ABC, ABC to BC, BC to C, C to CD, and then retaining CD. All right. So, but it would have been still a valid tree decomposition if I took C instead of B here. But the option is saying B, so we will take B. Okay. So far, so good. So this is the end of the first question. So today we are very lucky. We have only 4 questions. And yes, this question is, yes, just the continuation. So now we have the nice tree decomposition. Given the nice tree decomposition, uh, oh, so this is counting. This is even easier. So how many? All right. Okay. So how many in this? So this is the final nice tree decomposition. So now you classify the nodes as to which one is join, which one is introduce, which one is forget, and which one is leave, and then give the count.
so introduction, introducing nodes are five in the counts, and there is only one five among the options. So I think that the option B is correct. And do we need to check the forget and the other options also?
No, no, no. Yes, yes. Once you have already checked that there are 5 introduced nodes, the other options are ruled out. Okay.
Yes.
So in fact, we have done 50% of today. So this is the main purpose, as I said, of doing this nice tree decomposition is to find dynamic programming algorithm. So what is the question? So we have seen in the previous session that one can find the maximum weighted independent set in a tree. Okay, in polynomial time using dynamic program, but it is not possible to do so in a general graph. So here you are given a tree. It's a very simple graph, 3 nodes, A, B, C. Weights are also given. So weight of A is 1, weight of B is 5, weight of C is 3. So you have to give me a subset of these nodes such that the sum of the weights of the nodes in the subset is maximized. So what will be the answer for I mean in this graph, what is the maximum weighted independent set? Which nodes form the MIS?
You see, there is only one option because the vertices A and C are not connected. I do not have liberty of selecting any other pair of the vertices here because those vertices are connected, and the sum came out to be P plus 1 for here.
So which two vertices, A and C?
A and C. I do not have any other option with me. Why so? Because all other vertices, there is connectivity in between the vertices. If I go for any other pair of the vertices.
Okay. But a single vertex can also be considered as an independent set.
Yes, I did not think in this way. Yes, so even vertex B alone, yes, so
Yes.
its weight is 5. So yes, so maximum weight independence and then
Yes, yes, yes. So that is true. But The idea of this question is to, uh, you know, look at the tree decomposition, nice tree decomposition based dynamic program. So after doing this dynamic program, they will also say that look, for this simple graph G, easy. I mean, simple means simple to see. Uh, B, and taking the node B alone is the right thing to do when you are intending to find the maximum weight independent set. That is exactly what they're going to do. But they're doing it sort of using it some DP table, they're computing some entries. So if there is a large graph, then you cannot look at the graph and say that, okay, this is the maximum weight independent set. Then you have to write the algorithm, write the code, and then you have to execute the code, and then you will find out. All right. So we will see how, in general, with the help of this small example, we will see how DP can be used to find the maximum weight independence. So last time also we had seen a DP. We had seen a DP where we said that, okay, if you're taking a node, let's look at the previous DP for completeness. So with this DP also one can find the maximum weight independent set in a tree. Huh. But before looking at this DP, just to recall what we have already seen, let's see last week's DP. Because that was much easier. This is slightly more complicated. So, but although it is demonstrating a different thing, nice 3D composition. So this is a picture that we had. So we had this graph and we computed two table entries. So we computed an array A and array B. So where array A was the maximum weight independent set. So A of V was the maximum weight independent set in the subtree rooted at V, denoted as TV. And B of V was the maximum weight independent set in the same subtree rooted at V, but not containing V. So we could do a bottom-up computation. So from the leaves, we could do a bottom-up computation from the leaves towards the root. And we saw that how to fill these two arrays A and B. And we saw that while computing the value, let us say B of B at some point, then we will say that, okay, you're either taking a vertex. If you're taking a vertex into your independent set, then you are not taking any of its children. Then you can take the grandchildren. But if you're taking not taking a vertex, then you can take the children and so on. Because it's a tree, so we could build up this table bottom up, and then we uh, uh, computed these two missing entries. So what is the final entry corresponding to the maximum weight independent set? It is A of R. R is the root, so that is the maximum weight independent set rooted at R. So we recall that using some recursive formula, it is possible to fill up this table. So very straightforward. Then we saw that in a different kind of graph, which is called a subgraph of grids kind of graph. Again, this is sort of like a tree. We can do similar thing using DP. Maximum weight independent set can be recovered. But if the graph gets more complicated, we know that this is NP hard to compute this maximum weight independent set. Today, we will see a different DP. Although it is considerably more complicated. So that is why I think they have given a very simple example, 3 nodes. So let me copy this graph. So this is our input graph. And in this input graph, we want to compute the maximum weight independent set. Although we can see it, we can look at it and we can tell that B alone is the maximum weight independent set, but we will see it with the help of nice tree decomposition. And then we can answer similar questions if asked at all. Okay, so this is the graph. So I'll write down the weight. So B has weight 5, C has weight 3, and A has weight 1. Now let's look at how they have found the decomposition. So this is the corresponding nice tree decomposition. So this is question number 3. So here is a nice tree decomposition. So first let us verify if it is really nice. They have already labeled that which one is introduced, which one is forget, which one is, yeah, all the types of nodes are also introduced. So we can be fairly sure that this is indeed a nice tree decomposition. All right. So now we are interested in the finding this maximum weight independent set. Okay. So some table entries are being computed. So let me copy this as well. So we have to uh, uh, find the missing entries. All right. Okay. So this we can do. After that, we'll have only one question. So I think after the break, we'll have only one question. So we should be able to finish pretty early today. Okay. Okay. So here I'll have everything within the view so that we can do the computation here itself. Okay. So what all things are missing? So this entry is missing. So this entry is corresponding to the root R and the empty set S, and this entry is missing corresponding to T2. T2 is this node and AC. This is missing corresponding to T3 and B. So T3 and B, and what else?
Um, T2 and A comma B is also missing.
Yeah, yeah, this one, right? Yes, yeah. So in this table there are two missing entries. This table there is one, and this, so four things have to be computed. So first thing is, what is the recurrence? How shall we find M? Okay, so yeah, that is all about the question. I'll write down here. So we have to understand the recurrence, and that will be the decision. That's all. It's nothing more. Okay, so let me write down exactly the definition. Okay, so here is the definition. Okay, so M of P comma S, yes, it is the maximum possible weight. Okay, of a set of vertices, of course, S cap, such that uh, okay, so for a vertex, just a second, we should have more space here. I'll write down, then I'll explain. Such that S is a subset of S cap, which is a subset of VT. VT is something I will define. VT and S cap intersection XT is S, and S cap is independent. There are three parts to it. We will disassemble the three parts and understand each of them. Okay. Huh. Mm, right. So S is a subset of the vertices. So T is a node in the nice tree decomposition. So an entry M is taking a parameter T, which is a node in the tree decomposition, and a subset of vertices S. So corresponding to every T comma S, there is an entry M. Okay. So what does this entry signify? So it signifies the maximum possible weight of a set of vertices S cap, such that S cap is a superset of S, and it is a subset of VT. So VT is just a second. So what is VT? VT is the union of all the bags present in the subtree of T rooted at T including XT. Okay. So for example, if I'm talking about, say if I say T, so for now let us say I am assuming T is T2, then V of T is the union of uh, all the bags present in the subtree of T rooted at T. Then I'm looking at the union of all bags uh, uh, for all nodes in the subtree rooted at T. Okay, so look at it visually. So T is T2. So T2. So in the subtree rooted at T2, we have all these bags. So the union of all these bags together is V sub T. That's all. Okay. And XT is simply the bag of T. So in this case, T is T2. So XT is simply the bag of T, that is ABC. So XT is just the bag of T as usual. Okay. So is the definition of VT all right?
Yes, can you explain, I mean, the terms VT and XT again?
Yeah, so VT is for example, if T is set to T2,
Mhm.
then in the subtree rooted at T2, we have all these bags,
Including T2 or excluding T2?
including T2.
Okay.
Yes, including T. Yes. Then all these bags contain so many nodes. These nodes together is VT.
Yes.
And only the bag of T is XT.
Mhm.
So now the definition is the following. So you want to find an S cap. This S cap realizes the maximum possible weight such that S cap is a superset of S, but S cap is also a subset of VT, and S cap intersection XT is S. And of course, all the vertices in S cap should be independent. So this is the definition, but once we will look at the computation, things will become more clear. Okay, so even if you don't understand the definition now, we will understand this once we will run it. Okay, so we have to uh, just a second. We have to compute this missing entries.
So, yes, but then it seems from here that XT is same as S only. because if xt is the content of the vec t2, and if the intersection of the s hat and then xt is equal to s, uh, so probably the definition of xt needs some change. But if xt is the bag of the t2 only,
So let me recheck it. So maximum possible weight of a set S cap such that S is a subset of S cap, which is a subset of VT, and S cap intersection XT is S, and S cap is an independent. So third component is also there.
third is there fine, but then what would be the meaning of the intersection of s cap and then xt, and it becomes equals to s if xt itself is s only? Because if xt is the, I mean, the content of the vec t2, right? And what is s here? Uh,
So it is not necessary that all the vertices in S are independent, all the vertices in XT are independent. That is also not necessary. So
okay.
let us first compute one of these entries, then we will be clear. So let's compute this entry. Okay.
Yes.
So let us compute this entry. So this is entry. What is this entry? So this entry is m of t3 comma, instead of s you will write b. All right. So now first look at t3. So t3 is this node. Okay. So you want to identify a maximum possible weight set S cap such that what is S? S is B. B is a subset of S cap, and S cap is a subset of all these things taken together. And S cap intersection AB. AB is the bag of T3. It is S. Okay. And S cap. So first, yeah. So let's only worry about these two things. So you want to find an S cap such that S cap intersection XT. So XT is AB here. This is S. Okay, so let us say, can I take both A and B? That is the first question. So you are asking, yeah, so you are saying that it can be both A and B. So X is AB. So, but if AB are both are taken, then independence will be lost. So you can take either A or B and ensure that S cap intersection X is S. So now we have already seen that S cap can be either A or B, because if both A and B are taken, so X is A and B, then independence will be lost. There is a direct edge between A and B.
So I could not understand this from this figure. However, if I take say s cap is equal to a, then this condition, this intersection condition will not get fulfilled. So since xt is equal to a comma b and s is equal to b, so therefore s cap should be, I mean, should comprised of only b. A is not allowed. A won't work.
Yes. Uh,
So
y- so come again. A is not allowed. Why?
because if I consider say s cap is equal to a, then if I take the intersection of a with xt, and which is a comma b in this case,
Yes,
then the value will come out to be, I mean,
that is
a.
true. So you want this to be S. S is already B.
Yes.
Then how can A be S cap? So A is already also ruled out. So clearly S cap has only one choice. That is, it has to be B, and therefore we'll just populate this with the weight of B. So weight of B is 5. So therefore this entry should be 5. But this is not how you should do. I mean, I did it just like that, but there is a formula. Okay, so far conceptually we have understood that what is the way to compute a particular entry, but there is a formula for it, so that you can you can derive this entry from the entries that you have already calculated. So you have calculated, so you're always building this DB table bottom up. So now when you are at T3, you already know what are the table entries corresponding to the below level. So you know this T6, T7, these things are already known to you. Now, although this is correct and correct only, but let us use the DP table. So there is a recurrence. I will show you the recurrence now. Where is the recurrence? Huh. Okay, so I'll now write the, of course we have computed it, but let's do it by the recurrence also. So first identify that what kind of node, what is the classification of this node T3?
Yes, so this node T3 is of joint type.
Yes. Now we'll check that what is the uh, formula for a joint type node. Oh, what happened? Just a second. Come on. Huh. So here is the formula. So if T3 T is of type join, then here is the formula. Then M of uh, T comma S equals M of Y1 comma S plus M of Y1 comma Y2 comma S minus weight of S, where Y1 and Y2 are children of T. Okay. So now we will apply this and see whether we get the same thing. So what are the children of T3?
So children of T3 are T4 and T5.
So now we want to write the same thing. So M of T3B should be M of T4 comma B plus M of T5 comma B minus weight of B. Okay. So what is M of T4 comma B is already computed in this table.
Yes.
It's 5. Similarly, here is M of T5 comma B. So 5 plus 5. So this is 5 plus 5 minus what is weight of B? That is 5.
Yes.
So we can see that we got the same answer. So yeah, so some formulas are there. So for a join node, this is a formula. Okay. Now, if you ask me why this is a formula, then I have to give it a thought.
So if I agree to this, so somehow, but I have a different question here. That in this maximum weight independent set problem, and what is the complexity class of this problem? Say if it is NP-complete problem, then can we view this problem as a combination of which two problems? Like say independent set is one problem, and simultaneously we have to maximize the sum of the weights as well.
So
So
there are two versions. One is the unweighted version, where all the nodes have same weight. That means you can think of a weightless situation that all the nodes have similar, I mean, exactly same value. Then it is called the unweighted maximum independent set, and the objective is to select the maximum number of nodes such that no two nodes have an edge between them. Whereas in the weighted version, The objective is to select a subset of the nodes such that the sum of the weights of the selected subset is maximized. So both the problems are NP complete in the general sense, in the case when the graph is not restricted to anything. But for tree or some special classes of graphs, using DP, one can find the exact solution in polynomial time.
Okay.
So in fact, it is one of the most difficult problems. So for an n node graph, so in a graph, if you just select one node, that is an independent set. So if you say that, okay, I do not know, this is a very complicated graph, but I can give you an independent set, you can just output one node. That is a valid independent set. Now, it might have happened that all the nodes are independent. That means there is no edge in the graph at all. So if you have a graph where there are no edges, then what is the size of the independent set? There are n nodes.
Yes, so the size would be 1, and again it depends on. So no. The number of the nodes available here. I mean, we do not have any edge here. So all
Yes,
the
yes.
experiment of one another.
Correct, correct,
So
correct. Yes.
number of nodes.
So in an n node, so at the most, so the size of the maximum independent set, most it is called MIS for short. MIS. The size of the maximum independent set is at most n. So if all the nodes are independent, that means if there are no edges in the graph, then the size is n, exactly n. But if edges are introduced as so when the graph becomes denser, then the MIS decreases. For example, what is the MIS in a complete graph? What is the maximum number of independent nodes in a complete graph?
1.
It's one only. So the sparser the graph, the more the independent set, the larger the independent set, and denser the graph, the smaller the independent set. But irrespective of whether the graph is dense or sparse, you can always output a single node, and a single node is a valid independent set. Okay. So now, uh, if I ask you that if you output a single node as your independent set, then what is the approximation factor you have achieved? So you know that the problem is NP hard in general. So we are only hopeful of getting some good approximations. So I have discussed, let us define it. Okay. So what is an approximation factor?
1 by n.
Yes. Yeah. So in this case, if you just uh, output a single node, then if the optimal independent set was n nodes, then you have done at least 1 by n factor close to that. So if your solution is at least some 1 by c close to the optimal, then you say that you have a c approximation. So in this case, you have an n approximation. So it is also known that maximum. So a trivial approximation is an n approximation for maximum independent set, and it is known that getting better than this, slightly better than this, for any n by n to the 1 minus epsilon approximation, for any epsilon greater than 0, is not possible in the general sense, in the general graph. So it is so hard that other than doing the naive thing of outputting a single node, whatever clever things you do, beating n approximation and getting a slightly better than n approximation, which is n to the 1 minus epsilon, is not possible.
Do we have some proof of it or what?
Yes, yes. It is there. It's been proved. It's known to be. I will tell you. Let me tell you what is the reference. Uh, Proof of n to the 1 minus epsilon hardness of maximum independent set in graphs.
So, but then this independent set problem is getting reduced to so many other problems, like say to the click problem and to the vertex cover problem. So, how do
All
we have?
this. Oh, so you're saying, oh, so those reductions are not approximation preserving. So if you have an approximation preserving reduction, then you say that, okay, that approximation hardness is also applicable to the new problem that I have reduced to.
Okay,
I will tell you exactly what is the reference. Where is my this thing?
so I have a little one more query here that we are using DP here. Why so? Because this problem is in
Tree
the
like.
form of P.
Yes, yes. Because it is a tree. So in a tree, you have this nice thing about the parent level being independent from the grandparent level. Sorry, the grandparent level and the, let's say, normal level. So if you have a reference level, it is connected to the parent level and the child level, but the reference level is not connected to the grandparent level or grandchild level.
Yes, yes.
Yeah, so this is there is a reduction. But let's take a break now, and in the break, I'll find out this nice proof that n to the 1 minus epsilon hardness of maximum independent set.
Yes,
And
yes,
this
sure.
is the end of this question. So other entries can also be computed similarly. So we have one more question, but we can also see that what are the formulas, DP formulas for introduce node and forget node. So we have computed MT3B only. We know that these two are the possibilities. Okay, the one more question is left. So let us come back at 7. What time shall we come? Shall we come back at 7:25?
Yes, yes, sure.
Can you hear me?
Yes, yes.
Oh, so I found out something more interesting. So this proof that there is no 1 minus epsilon approximation for the maximum independent set of in a general graph. This is by due to Johann Hastad, and there's a paper. This paper is called the just a second. Yeah, so this is a 2001 paper. It's called the sum optimal inapproximability results. Okay, so this is published in 2001, and this is the most, I would say, I mean, this is arguably the most prestigious journal in theoretical computer science, in Journal of ACM in 2001. And more interestingly, for this paper, he received the Gödel Prize in 2011, Johann Hastad. So
Okay.
this is not only about this result, it contains other results, many inapproximability results. And if you look at the abstract, it is so interesting. It's very small. And I just looked at the ACM citation in honor of Johann Hastad, and maybe it's a nice read. It's just 2 pages. It says that before Hastad published these novel findings in the Journal of ACM in 2001, such optimal inapproximability results seemed beyond reach. And then the PCP theorem, PCP theorem and other things are also related, which you can read from this citation of ACM. Okay, so this is slight digression, but it's a nice thing to know.
Yes, and it is 62 pages long.
You should only read the citation, then you'll get an idea of how it is like. Uh, but the abstract is 2 sentences. Uh, Fine. So where are we? Okay, so I realize that so so the next question is just similar question. So instead of the maximum independent set, we have the three coloring problem, and the DP is considerably more complicated. And going over the DP will not help because it will be just repetition of what is in the video. Rather, we should rather I would say that a better utilization of time would be to look at computing because we have understood, we have disassembled the pieces of this maximum weight independent set problem in terms of the nice tree decomposition. Uh, we should better analyze the other three nodes, the forget node, the introduce node, and leaf node, and how we can fill these entries. I will, for the rest 15 minutes or so, I will go through computing the remaining entries because this question is even it's similar in nature. Again, you have this nice tree decomposition, and then you have to define what these recurrences are. So, and that is not going to happen in 15-20 minutes for sure. And let us look at something which we understand, which is not half baked. So let's go back.
So
Yeah.
I have a question here that since we are studying tree decomposition and Treewidth topic in this session as well as in the previous session, so I mean, what is the use of this idea in the parameterized algorithm? How does it, I mean, apart from helping us to find the solution of some of the problems which are in the specific form, like here, if the problem is given in the form of a tree, then we could solve it in the polynomial time. What else this idea of the tree composition gives us to I don't know, to solve to address interactive.
So there are many problems. For example, this next problem, so your question is, uh, what are the application areas of nice tree decomposition in the context of parameterized algorithms? Uh, Let me
Yes.
give a precise answer to that. Let me open the textbook, and in the textbook there are multiple nice examples. Uh, just a second. Huh. So this is a new laptop. It's slightly. I want to go to this page number. Slightly cumbersome. So I can see that at least three problems. Uh, so other than weighted independent set, this coloring problem, this dominating set problem, and Steiner tree problem uh, have been handled using this 3D composition. And along with that, the clever use of balanced separators have helped in designing FPT approximation algorithms for a number of problems. So beyond the problem that we're discussing, I think I think a more philosophical thing would be to see that if you can find a structured way of decomposing the graph into this nice tree decomposition, then this DP enables you. In this case, of course, we know how to find a polynomial algorithm, but in many cases, uh, best we can hope for is probably an FPT algorithm. So similar thing executed on other problems could give FPT approximation algorithms using this concept of tree decomposition. I'm not an expert in this area. I just maybe I give more generic answer than what you were expecting.
In this course, apart from the FPT thing and parameterization thing, what else is important? So I mean, so that
Okay,
we
so
can, yeah.
so in this course, what are the advanced techniques other than these?
Yes, yes. Your video got freezed. In case if you are speaking something, then your video is freezed. And
Oh, my video is okay. Uh, I think I can see myself
yes, yes.
moving.
Now I can see you, but then there
Uh-huh.
is some. Yeah.
There is some echo also, I think.
Yes, it is. It is better now. Yeah.
So honestly, in this course, what else are going to be discussed? That is, I can only look at the syllabus, and maybe I won't be able to say anything more than what is the syllabus. So in the syllabus, there is some other improved dynamic programming based on tree decomposition I can see, and there is some use of something called sieves and convolutions, which are some algebraic techniques that can be used for designing FPT algorithms. There's some advanced kernelization algorithms are there for connected vertex set, max CR set, and feedback vertex set, and these problems. Some cuts and separator based algorithms which can give nice FPT algorithms for directed vertex set, edge multi-way cut. These are also going to be discussed. So I am only looking at the syllabus and telling you.
Yes, yes, because I'm in search of some flowchart type of the things wherein how to handle the difficult problems in computer science. Some guidelines are given that okay, if these are the characteristics of this difficult problem, then probably we can go for the generalization thing or the parameterization thing or for the FPT thing, or we can go for approximation or I mean all those techniques which are used to tackle or handle the hard problems in computer science something guidelines or in the form of a diagram or the flowchart. So
Mhm.
I'm looking for that stuff. When I searched it on the YouTube, then even though I did not see that video completely, but I found one video of Professor Nildara Mishra, long, I mean, years back video wherein she delivered a talk on that how to handle the difficult problems in computer science.
Okay, okay. So if you have a link to that video, you can share with us. I'll check it.
He says, I'll mail it to you.
Okay, okay. You can also share in this chat box also. That is also fine. Anyhow, you find it. So I do not really know that what is a rule book, what is a uh, algorithm of whether there exists a deterministic algorithm to find out which technique will work for which problem. In fact, when you are looking at a new problem, there's some echo on your side, I think. Uh, yeah, thank you. So when we deal with new problems, when a new problem is at hand and we do not know how to go about it, then maybe 10 different techniques one could apply, but probably nine of them will fail. Only one of them, one of the techniques will work. So in such situations, if you're naive and then you apply all the techniques and then you discover for yourself that which one is the right technique and which are the nine techniques that will fail. But with experience and intuition, an intuition is generated, an intuition is developed, which will help you rule out the techniques which are less likely to work. That comes with experience, and I have seen people who can do it very well and some people who cannot do it very well. So I do not know whether there's a deterministic way of deciding which techniques you should apply right after looking at the question. But when you have sufficient experience, so you, for example, in MIS, the fact that for tree one would apply a dynamic programming kind of thing makes more sense because of the inherent nature of tree. And once people realize that trees are more amenable to DP, they will apply DP more often to tree-like questions. So, but if you have seen something which you referred to, then I would also, okay, you have shared with me. Let's see what it is about. Cheat sheet for hard problems. Oh, wow. So this is a nice thing, but I do not know. Uh, okay. It is in one of the conferences. Okay. Wow, this is a nice research. So I did not know that such a thing could exist. Uh,
But
yeah, I mean,
actually, yeah, but expertise is required to understand her talk.
hmm, 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 hmm. Okay. So my gut feeling is when there is a new problem which is hard, and then to some extent it might help this cheat sheet. Uh, but whether there's a sure shot way of eliminating certain techniques and applying only a few, that I do not know whether such a thing exists. But I'll find out if such a thing exists. I'll share with you.
Sure, sure. Yes.
So let's look at. the problem at hand. So far we have computed only one entry which was missing, which is this thing, that is this one. So let's look at, so this is a join node T3. How about T2? T2 is an introduced node. So let us compute something with respect to T2. So T2 and AB we can try to compute. Uh, yeah. So T2 is an introduced node. So first I'll tell you what is the formula, that is the recurrence for an introduced node. So we know what is the recurrence for a join node. We'll not stretch it too far today. Week 6, okay. Desktop. So for an introduced node, the formula is the following. It's so let's recall what is an introduced node. So in an introduced node, you have a situation like this. There is an additional vertex with respect to the child bag, and uh, okay. So how can I write something which is feasible and fitable here? Uh, so what I can do is I can move things down. Oops. Uh, this thing can be moved down. Yes. Yeah. So this much space is sufficient for this. So you're interested in computing m of t2 comma a comma b. So what does it mean? It means that you want to find the oops, yeah, now it is visible, the maximum possible weight of a subset S cap such that AB is a subset of S cap, and it's a subset of all these elements in these bags, and S cap and the bag of E2, uh, their intersection is S, and S cap is independent. So we can do all these things, or you can apply the formula. So the formula is the following, that Y is a child of T2. So let me write the formula first. So it's like M of T comma S. So this is for a introduced node, is one of these following. So this we can handle later. Let me write the general formula. So M of T comma S. So this I'm writing for an introduced node. This is equal to M of Y of S. Y is a child of T. So it's like this. If V is not okay, so V is that node which is introduced. So in T, V is introduced. So V is V is introduced at T. I'll write it down. Element V is introduced at node T. So V is not in S. So what is introduced in T2? In T2, we have introduced.
C has been introduced.
Okay. So we are computing AB. So yeah, so this case will apply. Uh, uh, V is not in S. Okay, other cases I will write S minus V uh, plus weight of V. This is a situation if V is part of S, but V has no neighbor in S. So this is if V is part of S, but V has no neighbor in S. The other situation is S contains V and all its neighbors. So then if you insist on, you cannot pick independent set with a vertex and its neighbors. All its neighbors. Okay, so which case applies in this case? So we have T2, an introduced node where C is introduced, and the yeah, so S is AB, so C is outside of S, so V is not equal to S is applicable. So we can simply take M ys. So y is the child. So what is the child? Child is T3. So we'll just take this is equal to M T3 AB by virtue of this formula.
Minus infinity.
Where is that? T3 AB. Huh. This is minus infinity. Okay. So what does it mean? Now let us understand that what does it mean? So we are asking that what is the maximum possible weight of a set S cap such that uh, 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 S, that is in our case A comma B, is a subset of S cap, and S cap intersection XT is S. So XT itself is ABC. This one is AB. So you can take A comma B, you can take A, no, no. So you have to ensure that this happens. So you can take AB or you can take ABC at the most. Right? Now AB, if you take independence, will not be ensured. Mm, let us see the answer if we have done the right thing first. So yeah, this is minus infinity. Let's, what is the answer? 5 minus infinity. So this is correct. But what is the meaning of MT2AB? Let us appreciate the meaning. So we want to appreciate the meaning of this. So from this definition, that why is it minus infinity? Can we just look at it and tell immediately? S is A comma B, XT is ABC. So any S cap intersection ABC, you want it to be AB. So AB you want to take for a fact. AB will take, and you will take something else. Okay. So as soon as you take AB, it is no more independent. That is the problem. That is why it is minus infinity. So you want to take an S cap such that S cap intersection ABC is actually AB. So you must take in S cap AB and some more things. But as soon as you take AB, the independence is lost because of this edge. That is why intuitively also this is minus infinity. Yeah.
Yes, yes. So like S cap here is ABC, uh, and XT here is uh, XT here is ABC again. So if I take the intersection, then the value comes out to be ABC. But then this ABC is not equals to AB, or even if I take the subset of the S cap as a subset of the BT here, so at the most I can take AB. If I take S
Yes.
cap as AB, and if I take the intersection of AB with ABC, then the value comes out to be AB.
Yes.
But yes, so but then this AB should be independent. S cap should be independent, and AB is not independent here. So yeah, the value is independent. Makes sense. Yeah.
Yes. 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 So finally, our target is to output B, which is the maximum weight. This thing. So let's look at the answer. So finally, they say that okay, they have found these four missing values, and I think yeah. So the last missing value is four. So corresponding to the root of MT is four, root of B is five. So let's write it down. So this value is found to be four. So this is four. So in the last there is at the root level, the computed values are 4 and 5. So that is why the value 5 is taken, and that is the independent set, maximum weight independent set. Yeah.
Yes, yes. And even from this definition, so this time I can take the value of S cap as A comma C only, no other way. So because xt is ABC, so if I want to make this intersection is equal to S, so I can only take the value of S cap as A comma C. And if I take A comma C here, so then I'll get an independent set of the weight is equal to 4.
Right. So you're talking about this missing entry, right?
Yes, yes, yes. No, not this one, but then this one. What was that? The T2 comma S for AC.
Oh, you're talking about this.
Yes. So this value should also be equals to 4, I guess.
Right. Okay.
Yes.
Yeah, this is S is A comma C. So you have to take A comma C and A and C together 1 plus 4. Huh.
Yes.
1 plus 3. Yes, 4. Okay. So this is also 4. So yeah, I mean, with some intuition, even without going through these formulas, yeah, this is 4. Yeah, with some observation, but based on the discussion we had, we should be able to solve such kind of questions. But it is more complicated than the previous DP. And the next question is even more complicated, so I didn't go over it. But you are right that, yeah, I mean, we are we are learning this thing. So in other settings, there could be no other way to sort of uh, solve a problem without resorting into a nice 3D composition. That's why probably this is something we should have in our mind. Okay, so I think this is we are towards the end of today's session. Next class, we will discuss these questions. Yeah, so again, some tree decomposition and application of tree decomposition. So we will see more of tree decomposition and how it helps us design FPT algorithms. What is next? Okay, then there's a change. Then there is some integer linear program stuff and other things. So I think, yeah, I mean, we are halfway through the course. 6 weeks are over. So thank you. Thank you for joining today, and I hope to see you again next week.
Thank you so very much. And today's session was so very interesting. Thank you so
Thank you.
much.
Thanks a lot.
Good night.
Good night.